Got it. Now Mike Zabrocki of York University is here to give lecture 2 in this series on symmetric group characters as symmetric functions.
Thank you, and yeah, thanks for this organizing this, because it's very nice. So I've written up here on my first slide the title, our names, but also my agenda for today. So hopefully I can get through all of this. Depends on how fast I go. I don't want to go too fast, but a lot of things that I'm going to say today are just straight from Bruce's book on the symmetric group. So it's like I'm not going to go too deeply on anything except for a little bit of extension of this of the Frobenius character map. So everything else is something that you would find in usually in a graduate course. I took a course similar to this in graduate school, and just going to cover the modules and characters of the symmetric group, the Frobenius character map, and then I'm going to apply it to something called the restriction problem, which is the problem of decomposing an irreducible GLN module into SN modules. So what Rosa set up last time was she gave a description of GLN modules and GLN characters, and I'm going to say, how do we apply the representation theory of the symmetric group in order to decompose a GLN module as a symmetric group module? And I'll make a connection with the Kronecker product, and that brings us back to what I'm going to start with is a question that Rosa posed to me in 2012. She wrote me a message and she says, "Are you busy? I have a neat problem, but I need your help." And so we set up a Skype call, because there was no Zoom at the time. And the question she posed to me is there a basis of the symmetric functions that has as structure coefficients the reduced Kronecker coefficients? Now, Rosa covered this in her talk the other day, is what are the reduced Kronecker coefficients? But what her question was, is there a basis B lambda times B mu gamma, and then the reduced Kronecker coefficients, she denoted G bar lambda mu B gamma. So is there a basis with these structure coefficients? And surprisingly, this question was linked to a problem that I had been thinking about for several years, and it's this restriction this restriction problem that I mentioned earlier. And so I want to go through the representation theory of the symmetric group and see if we can make this connection a little clearer. So let me just want to make sure that I'm not going to have somebody call me in the middle of the talk. Okay, here we go. Okay, so let me start by just going over kind of what is a module, an SN module. An SN module is a vector space with a symmetric group action. So examples, the easiest one is called the trivial module. So we have V1 is equal to the span of a one-dimensional module. So there's one vector, and then when the symmetric group acts on V is equal to V. Another example is a one-dimensional module again, sigma and Sn, and sigma acts on W, though, this time by multiplying by the sign of the permutation. Slightly more complex example is a permutation module. So we have a basis V1, V2, Vn. And the action of sigma and Sn is that sigma of Vi dot Vi is equal to V sigma I. And then this, when Rosa gave it as it's also a GLN module. And when she gave it as a GLN module, she said that that was the defining representation. So the permutation representation and the defining representation are kind of the same thing. So my fourth example is slightly more complex, but Rosa had given it in her talk as well. It's the span of monomials in VI. So V1 to the A1, V2 to the A2, Vn to the An, where A1 plus A2 plus An is equal to D. And this, she denoted Sim D Cn, because it's also a GLN module. And sigma acting on V1 to the A1, Vn to the An, is going to be V sigma 1 to the A1, V sigma n to the An. So now a character of an Sn module, character of an Sn module is a map from the symmetric group to the complex numbers. And then chi of sigma for sigma and Sn, chi of sigma is equal to the sum. And you run over some basis of the module. So it's a module B, and it has a basis, BV, and it's the coefficient of B in sigma acting on B. So I'm going to summarize kind of the elements of characters that we need. So theorem, and this is, I love as a reference, Bruce Sagan's book, The Symmetric Group, because it just does it as simply as you could possibly do it. It's there because there are lots of elements of how you prove this theorem, but the theorem is characters characterize. Okay, that is, the characters act as a signature for a module. So the first thing we need is that if sigma and tau are in Sn and sigma and tau are in the same conjugacy class, then chi of sigma is equal to chi of tau. So I should say chi is a character for a module, an Sn module V. Okay, so that means what we can do is that if sigma has cycle type mu, so it has a cycle of length mu1, a cycle of length mu2. Then we're going to denote this by the psych sigma is equal to, and then we can just specify the character evaluated at any element of the cycle type by chi mu is going to be chi of sigma. So 2, there are irreducible SN modules. Which we're going to denote as chi lambda, and they're indexed by partitions lambda of n. So I'm going to say lambda is a partition of n. It's my notation. And the irreducible characters, the characters of those irreducible modules, irreducibles are denoted chi lambda. So we're going to evaluate these. These are functions of the elements of the symmetric group, but we can specify just the characters at representative elements of the classes. So these are class functions. 3 is that there exists integers m lambda v in z greater than or equal to 0 for each lambda partition of n, such that v is a direct sum, isomorphic to a direct sum for lambda partitions of n, s lambda, m lambda v. That is, every SN module is isomorphic to a direct sum of irreducible SN modules. And this is true if and only if the character is equal to the same sum of the irreducible characters. And then for the symmetric group characters are encoded in the symmetric functions. So I'm going to just use, without setting up a whole lot of notation, the Schur functions, the power sums, and connect them with these characters in that we have S lambda is equal to the sum over mu partitions of n, the irreducible character evaluated at mu, p mu over z mu. And Rosso already gave this formula. P mu is equal to the sum over lambda partitions of n, chi lambda of mu s lambda. And those z mu's are integers. So z mu is equal to the product over I greater than or equal to 1, mi lambda. I think I'm poorly choosing my notation. These are the multiplicities, I to the mi lambda, where I'm using mi lambda to mean the number of parts of size I.
Mike, I think you meant C lambda.
Yes. Thank you. So, and then the main takeaway that we need. So it's 5. Normally I able to fit this all in one page, but 5 modules are isomorphic. If and only if their characters are equal. In that sense, the characters characterize. And they act as a signature for the module. So once you have the characters, the character values, you can tell whether two modules are isomorphic. So I give as an example on the next page, 3 different modules. Presented them kind of in their matrix form, which these are called representations. So I'm given the representations, but on the right, I've defined modules V1, V2, and V3. And they are 3-dimensional modules. Their action is given by the matrices on the left. And I say one of these things is not like the other. One of these things doesn't belong. They all look very similar, right? As a matter of fact, they're essentially 6 matrices that are 3x3 matrices. They have integer entries, and they define an action on these spaces. It's not easy to see. I'm not going to prove that they are, but I say if you accept that these are in fact S3 modules, it's easy to tell which one is different than the others by calculating their character. So let me compute the character. I only need to compute it on the representatives, on one representative for each of each cycle type. So I can just do this one, and this one. And I compute the trace of this matrix, because that's going to be the sum over the basis, the formula for the character that I gave you earlier. It's the sum over the basis, the coefficient of the basis in action on the basis. So the trace of this is 3. The trace of this is -1. The trace of this is 0. For this one, the trace is 3. The trace is 1. The trace is 0. Here, the trace is 3. The trace is 1. Trace is 0. So what does that say? It says that phi1 is not isomorphic to phi2 or phi3. And phi2 is isomorphic to phi3. Or what I should be saying is, as modules, V1 is isomorphic to, is not isomorphic to V2 or V3. But V2 is isomorphic to V3. And if I give you the character table of S3, I just need to give the representative values of the character table. So these are the irreducible characters. And then I evaluate them at, I can evaluate them at 1, 2, 3. The identity, the trace is 1. If I do it at any of the elements of cycle type 2, 1. The irreducible character is 1, and then here it's 2, 0, minus 1, 1, minus 1. There's my character table. And then the fact that our characters, so that the character chi of V, say V3, we said is 3, 1, 0. And we see that chi V3 is the irreducible 2, 1 plus the irreducible 3. Similarly, chi of V1 is equal to the irreducible chi 2, 1 plus chi 1, 1, 1. So now I want to define Frobenius map, or the character map. I call it the Frobenius map because that's the name I was told when I first learned this, but I noticed that in both Sagan and in McDonald, they just say the character map without specifying who is responsible. So I didn't look up where it came from, but the Frobenius map takes an SN character and I mean, it can be any class function, and you evaluate for each value of, for each partition of n, you evaluate the character at the partition n and multiply by p mu or z mu. So I had given already the formula for the Schur function in terms of the irreducible characters. And what it says is that the irreducible characters are going to be mu partitions of n, pi lambda mu, p mu over z mu, which I said is s lambda. So now we can extend the theorem that I stated earlier and say that a module is isomorphic to a direct sum of irreducible modules. If and only if the character of V is equal to the sum over lambda partitions of n, m lambda V of the irreducible characters. And that's if and only if the Frobenius image chi v is equal to the sum over lambda partitions of m lambda of v s lambda. So it just allows, the Frobenius map allows us to do linear algebra inside the ring of symmetric functions. It just says that these two, the class functions and the ring of symmetric functions are isomorphic. So Frobenius map maps class functions onto lambda n, and this is symmetric functions of degree. Okay. So let's do an example. Whoops. There are my character tables. Okay. And I'm going to do as an example the same module that Rosa did in her talk, Sim2 C2. And it is the span of three elements, V1, V2, V3. Sorry, V1 squared, V1, V2, and V2 squared. Now, Rosa mentioned that it's a GL2 character. Is equal to S2 of X1, X2. This is X1 squared plus X1, X2 plus X2 squared. But we want to see it as an S2 character. Okay, well, if we evaluate the character at the identity, we take the identity matrix, and it has as eigenvalues 1 and 1. 1 and 1. So the character, this V, just to make it chi V of 1, 2 is equal to S2 of 1 and 1. And so if I plug in 1 and 1 for X1 and X2, I get 3. And 1, 2 has this as a its matrix of S2 sitting inside. So I'm looking at S2 sitting inside of GL2. And it has eigenvalues 1 and minus 1. So chi V of 1, 2 is going to be S2 of 1 and minus 1. And if I plug that into my X1, my GL2 character, that's going to be equal to 1. Okay, so then I look at the Frobenius map of my chi V, and this is equal to 3p11 over 2 plus 1 times p2 over 2. And then I can change bases because I know how to write power sums in terms of Schur functions and Schur functions in terms of power sums. And I get that this is equal to 2s2 plus s11. And so what it says is that V is isomorphic to S2 direct sum S2 direct sum S1. Okay. So what was I doing in this procedure? I have to take my elements of the symmetric group, I turn them into matrices, I compute their eigenvalues, I take their eigenvalues, I plug them into the symmetric functions. And once I plug them into the symmetric functions, I get the character values, and then I get the character values, and then I take their Frobenius map, and then I expand their Frobenius map in the Schur functions. So it's a lot of steps, but all of them are kind of standard. This is probably not the evaluation at eigenvalues is something you're going to learn when you learn the character theory of the symmetric group, but this is mostly all in the book, The Symmetric Group. But let's look at what I'm doing. And so if I have a D cycle, a D cycle looks like this: 1, 1, 1, and then 1, and this is the D by D matrix. And then on the diagonal, I have zeros. Off the diagonal, just off the diagonal, I have ones, and then 1 in the corner, and then zeros everywhere else. Yes. This has eigenvalues. The D roots of unity: 1 zeta D squared, zeta D to the D minus 1, where zeta D is equal to E to the 2 pi D. And what am I doing? I'm evaluating a symmetric function at these roots of unity. So I'm going to take a power sum, and I'm going to evaluate them at 1 zeta D squared, zeta D to the D minus 1. Right? And what is this? This is 1 to the K plus zeta D to the K plus zeta D to the 2K plus zeta D to the K times D minus 1. And you can work this out, that the sum adds up to D if D divides K, and it's equal to 0 otherwise. So I'm going to denote this thing right here equal to PK psi D. And then PK of psi gamma is just going to be PK of psi gamma 1 plus PK psi gamma 2. So gamma, I'm actually going to make gamma equal to, it's a partition, so I'm going to make it equal to 1 to the M1, 2 to the M2, and then D to the MD. Stop at D. It's PK psi of gamma, length of gamma. And so let's evaluate this a little bit further, right? I'm saying that this is the sum for D equals 1 to length of gamma, PK gamma D. And then if I group these by their parts, I'm going to say that this is I've used D one too many times, but I'm going to change this. Instead of D, I'm going to make that R. Doesn't quite follow my notes. R equals 1 to D And then I have M, R, PK of psi R. And this is then the sum of R divides K of R times MR. So I have the evaluation of PK, and it definitely evaluates to an integer all the time. And what is that integer? It's RMR. And if you notice, pay attention, that formula is something you can apply Mobius inversion to. So I'm then going to define P mu of psi gamma equals P mu 1 psi gamma, P mu 2 psi gamma, P mu and L of mu psi gamma. And then I want to define the Frobenius map, not just on class functions, but now I want to define it instead on symmetric functions. So my Frobenius map, I'm going to call something slightly different. I'm going to call it phi n. And you start in the ring of symmetric functions with symmetric functions. This is the n greater than or equal to 0. Psi n. Take all of the ones of any degree. It's going to take symmetric functions of any degree. Is it true that the eigenvalues are always roots of unity? You took a cycle in your example. Yeah. So when I evaluated at symmetric group elements, they will always be roots of unity. And phi n maps to lambda n, and my map phi n is going to take a symmetric function f, and it's going to map it to its Frobenius image. So this kind of shortcuts a few of those steps of how I was evaluating my character at roots of unity. So Fn maps symmetric group class functions to the symmetric functions of degree n. Phi n is going to map symmetric functions to symmetric functions of degree n. So let's do this as an example, just something that's slightly larger. I don't want to take something that I can't compute, but I'll take Sim2 C3. Remember, it is a GL3 module, but it's also an S3 module. Its character, so it's GL3 character, is S2 of X1, X2, X3, which is X1 squared plus X1, X2 plus X2 squared plus X1, X3 plus X2, X3 plus X3 squared. And now I want to kind of remember my character table. Save it for later. here's my character table 3, 2, 1, 1, 1, 1. And I'm going to compute the evaluation of S2 at 1, 1, 1. That's at the identity, right? The eigenvalues are 1, 1, 1. So I'm going to plug in 1, 1, 1 into my polynomial off to the right here, and definitely I get 6, right? Because there's 6 monomials, I get 6 when I plug in 1 for all of those variables. S2, 2, 1. And this one has eigenvalues 1, -1, and 1. And if I plug in to S2 of x1, x2, x3, I get 2. And then my final one, I have 1 zeta 3 and zeta 3 squared when I evaluate at S3. And so if I evaluate it at the 3 roots of unity, if I square each of those, they evaluate to 0. So this term, and this term, their sum is 0. And you can also check that this term, and this term also all sum to 0. So this is 0. Okay. So I have my character of my module V is 6 to 0. And if I take my Frobenius map of S2, I'm saying it's 6 times P111 over 6 plus 2 times P21 over 2. And either you do your linear algebra in your character table, or you do it in this ring of symmetric functions, and you say, oh, this is 2s3 plus 2s21. So that means if I add up 2 copies of this one and 2 copies of that one, then I get my character. That is, I'm saying that Sim2 C3 is isomorphic to S3, S3, S21, S21. Okay. So in general, this is an interesting problem. It's like, how do I decompose a GLN character as a symmetric group character, an SN symmetric group character? And it turns out that this problem has been studied in the literature, and every once in a while, someone will write something about it and then say, ooh, that's hard. Please, okay, here we go. Want to get to the end. I'm not going to probably present any results today. I'm just going to present the definition of what I got to. So the I want to make one connection between the character map, Frobenius character map, and the Kronecker product that Rosa was talking about last time. And so we take S22 and tensor it with S22. And this, in Rosa's example the other day, She said that this was isomorphic to S4 plus S22 plus S111. And so how did she do that? She looked at the character table of S4. She took this row of the character table, and she said that the character of the tensor of those two modules is going to be the dot product of their characters. So that is the character of 2, tensor 2, is equal to 4, 0, 4, 1, 0. And then she wrote this character here as the sum of this one plus this one plus this one. Okay. So more generally, if the character of chi v and chi w are characters of v and w, then the character of the tensor w is kind of the pointwise product of their characters. So that is chi of v, chi of w. If I evaluate this at sigma, this is chi v of sigma, chi w of sigma. And so we define a product on the symmetric functions that we call the Kronecker product. Such that P lambda over Z lambda, Kronecker product P mu over Z mu, is equal to the Kronecker delta of lambda is equal to mu P lambda over Z lambda. And then we do this because the Frobenius image of chi v, Kronecker product of the Frobenius image of W is equal to the Frobenius image of their pointwise product. Just do the calculation on the left, do the calculation on the right, you see that they're equal. The same thing happens with our other Frobenius map, this phi n of f, Kronecker product phi n of g is equal to phi n of f times g. Quite, just let's do the calculation. It's the sum over mu partitions of n f mu p mu over z mu, and I'm going to Kronecker product gamma partitions of n g gamma or p gamma over z gamma, and this is going to be the sum over new partitions of n f nu g nu G. He knew. It's he knew. So what Rosa's question was asking can now be answered in terms of this Frobenius character map phi n. We have for n really big, Sn lambda Kronecker product Sn minus like the mu comma mu. It's equal to sum over gamma G gamma lambda mu Sn minus size of gamma gamma. That's where the reduced Kronecker coefficients come from. Rosa said when n is really big, the reduced Kronecker coefficients are the limiting values in the Kronecker product. So now what should we take as our basis? Remember, I said I call that basis B lambda. I'm now actually going to give it a name. I'm going to call it S lambda tilde. And I'm going to take as definition for n really big, the inverse image of n minus size of lambda comma lambda. Of course, it's not particularly clear that this limit exists, but it does. Okay, why is that now? So if I take, so S lambda tilde times S mu tilde is going to have structure coefficients gamma mu r as gamma tilde. And what I will show next time is that this is if and only if their Frobenius image for big values of n, S lambda tilde times S mu is equal to gamma it's gamma tilde. Well, now why would we see the right structure coefficients? Well, because phi n has as Frobenius image phi n of a product of symmetric functions is phi n of S lambda tilde times phi n of S mu tilde. These are equal. And I'm taking here that S lambda tilde is the inverse image of a single Schur function. So I want to compute what is the symmetric function that is mapped to a single Schur function under this Frobenius map. And on the right-hand side, this is going to be the sum over gamma, the Kronecker coefficient, And on the left-hand side, this is equal to, sorry, this should have been Kronecker product. S n minus size of lambda comma lambda. Kronecker product S n minus size of mu comma mu. So this is doing exactly what I wanted to do if this limit exists. So that was the starting point when we started looking at this. And from this alone, you can compute these S lambda tildes. Because you can create the character table and you say, what is the pre-image of those elements? So the pre-image, so let's do it for the character table of S2. Phi2 of 1 is equal to P11 over 2 plus P2 over 2, which is equal to S2. So I have my S empty tilde is equal to 1. Phi2 of S1 is equal to 2 times P11 over 2 plus 0 times P2 over 2, which is equal to S2 plus S11. But I want it to just be S11. So I'm going to take Phi2 of S1 minus 1. And that's going to give me P11 over 2 minus P2 over 2. And so that says that my S1 tilde is S1 minus 1. Do this for the character table of S3, S4, S5, and you can calculate what these functions must be. I mean, I'm kind of at the end of my time, so I don't know. I can do the next character table to make sure it's clear. Maybe I'll start off next time. I'll compute the first couple with this method, so that you then have data. You have what the symmetric functions are. The next step then is to give a better definition than this one here, is the inverse image of a single Schur function in this character map. That's a terrible definition because you can't do a whole lot with it. So you can do some things, but you can't do a whole lot.
Thank our speaker. Very nice. Looking forward to seeing the table next week. So any questions?
Well, I guess I have one. Nice talk. So you're defining these symmetric functions as like a stable limit. Is there a monotonicity result? Like we could consider this thing for arbitrary n by taking, the Schur function attached, like a composition or something. But as n grows, do these coefficients like increase or decrease to the final value?
So what's going to happen is that they're mapped to, it always maps to a single Schur function or it's 0.
Okay.
And it uses like, well, so if you have you know how to define a Schur function with a short row,
right,
on a longer one. Well, they always evaluate to those. And so I don't know what will happen to the character values in those cases. I didn't really think about it, but
Yeah, because I mean, kind of for the stable chronikers, there's this result where if you add 1 to the first part of everything, you're gonna, kind of either stabilize or go up by 1. So do you have like monotone convergence somehow?
On the character values, that's an interesting thought. I hadn't. Seems like there should be, but I don't want to say yes or no without actually sitting down and doing a few examples.
Fair enough.
Well, there's no other questions. Is the next talk on Tuesday? Yeah, is that a Mike talk or a Rosa talk?
Mike,
Okay, I look forward to seeing Mike on Tuesday. So have a great.
Yeah, my plan is to go deeper into the symmetric functions. So it's like, I've got a definition, I'm going to give you better definitions, define all these bases and identify where the holes are yet.
That certainly seems like an intriguing new kind of function. So have a great weekend. We'll see you on Tuesday.
bye everyone.
I